So, we are now coming closer to the modern times. We looked at tectonic timescale changes where the movement of the continents, reconfiguration of the continents, mountain building was deforcing for climate change. Remembering always carbon dioxide is involved. We then moved on to orbital timescales where the changes in orbital parameters like obliquity, ellipticity and precession were the forcing factors. And we are now going to look at, we also looked at glacial deglacial, where again the orbital forcing initiates the advance or retreat of the glaciers that then kicks off feedbacks through carbon dioxide. We will now switch to what is called millennial timescale. A millennium is 1,000 years, so thousands of years of timescale. Why is this important? Essentially, we are now getting into what is called internal variability, which means it is being generated by the Earth system without corresponding forcing necessarily. So, it is like weather. As we said, the solar cycle, sun is going up, sun is going down on a daily time scale, but the weather can change several times during the day and it is going north south. So, there is a seasonal forcing, but within the season you can have multiple time scales. So, the feedbacks within the Earth system can create these time scales that are not necessarily there in external forcing. So, how are they generated and do we understand all of them? So, internal variability can also be often what is called stochastic or stochastic, which means it is non-deterministic. We cannot determine it. That is important because if you want to project into the future or if you want to make weather prediction, climate prediction, then you want to know what are the processes that are predictable and what are not predictable or stochastic. We'll use terms like noise and so on and so forth. So, it will turn out that the millennial timescale variations are very clearly recorded in many places around the world, high latitudes, low latitudes, northern hemisphere, southern hemisphere, and they are not very well explained with all the feedbacks we know of. And these kind of non-deterministic or stochastic variabilities can be a problem if you are trying to perturb the climate with anthropogenic activities, for example, and you kick off one of these stochastic processes, or it happens during the global warming. Can it amplify or diminish global warming, and what are the other runaway kind of feedbacks that can happen where you have rapid melting of the glacier or rapid advance of the glacier and so on and so forth. So, let us look at few of the evidences that are available and go through the processes that we have already looked at and then add a couple of more things like solar variability and see what are the explained processes and what are not explained processes. Okay. So, let us start with this where we are looking at evidence from Greenland ice core going back to 2000 years here, fairly short time scale. Again, we are looking at delta 018. Remember that when it gets more depleted in the ice, it is colder times. When it is getting warmer, it is losing delta 018. Corresponding to that, you have changes in dust concentration, more ice, drier climate, more finely ground up dust that gets carried away, and the drier climate also produces more dust, and rainy season can make finer silt, glacial times can produce heavier silt and so on and so forth. So, this is the previous interglaciation, this is the last glaciation, and this is the present interglacials. So, the last glaciation started around 120,000 years ago. It had extensive ice over the northern hemisphere, Antarctica grew more sea ice over Eurasia and so on. And you can see that it had these high frequency oscillations within it. So, even though glacier is growing and it is getting, so you are starting delta 018 here and you are reaching as high as minus 35 parts per mil, parts per thousand, and this slow change did not happen monotonically. There are jumps back and forth, and it will turn out that when you have heavy glaciation, especially the edge of the glacier can have fast variations, and there are various processes in the system that can create these feedbacks, but they are not necessarily easily predictable. That is the main thing we have to worry about. And you can see the rapid changes that happen in vegetation, dust concentration, etc., etc. So, these are the multiple time scales. We will define the time scales a bit better as we go further into this lecture. Was it only at on Greenland? Not necessarily. So, here is the North Atlantic sediment core showing percentage of polar species, which means cold water extends into the lower latitudes, and you begin to get plankton species growing that are cold or polar water species, which means somehow as the glacier is growing and shrinking on Greenland, you also have cold waters extending further south or retreating back. So, you have these percentage of cold water species increasing in this direction or decreasing. Okay. Now, you have time. Here we are going back to about 100,000 years. So, now we are focusing on the last ice age, and you can see that there are these rapid pulses which are anywhere between 6 to 9,000 years, 2 to 3,000 years. There are some 1500 year time scales in there. So, these are multiples of 1,000. So, we call them millennial time scales, and they correspond well to the variations of ice core record on Greenland, right. So, you can see there is more colder and growing ice and melting ice in this direction. So, there is something happening on Greenland and in the North Atlantic sediment. So, they must be connected through some atmospheric processes or the invasion of colder water further south, air sea interactions, and so on. So, there is a coherent variability between Greenland and North Atlantic sediment cores. That is something to remember. And we will see that these evidences also include the so called ice rafted debris, which means somehow chunks of glaciers are being carved off. Typically, they were being carved off from Laurentide ice sheet, which covered much of North America down to New York and so on, Middle America, and also in the Eurasian ice cover. So, you can see that various kinds of material like volcanic rocks, red sandstones, limestones, and other chemically distinctive rocks like these, which include iron stained quartz glasses, sandstones, and the various sources from Europe which were being eroded by ice. You can see the striations in these mountains and the carving of the soft material in between. So, as ice grows, it always removes the soft material, scours the ground, and creates things like the Great Lakes in Northern America, for example. So, even now Iceland is very active volcanic continent. So, you can see a lot of volcanic rocks were coming from there, lots of red sandstones and chemically distinctive limestones, etc., from all over the place. So, in the modern climate also you get a lot of ice carving, it is called, and where the icebergs break off from when the glacier flows and it jets onto the ocean and becomes the so called shelf ice, or there are other processes by which chunk of it can come off and start floating into the ocean. Of course, the most famous example is that the Titanic hit one of such big glaciers, and as you can imagine, ice floats. So, when there is a glacier, only about 10% of it is actually above the water, which means 90% of the glacier mass is actually below the water. This is how the ship got damaged, because there was a massive amount of glacier mass below the surface that the Titanic crashed into. So, there are times when lots of glaciers are being carved either from the Labrador Sea or the Jin Seas and coming down into the North Atlantic. Every time we say glaciers coming into the North Atlantic, you know that we are going to talk about changes in freshwater fluxes, which means changes in the amount of deep water being formed, which means the amount of heat that is being brought northward by the Gulf Stream and the North Atlantic current and so on. So, that means changes in meridional overturning circulation, which means that signal is going to become global, because the meridional overturning circulation is a global circulation. So, it is going to be transmitted to the Southern Ocean, into the Pacific and Indian Oceans. So, these are the processes, but the main thing we have to always look for, what causes those rapid changes, what is forcing those rapid changes. Is it solar variability, is it greenhouse gases, or is it something else? Because remember, these are at a much shorter time scale than tectonic time scales or orbital time scales. So, that is the critical thing to understand. Where else was the evidence found? So, again going back to the ice core from Greenland, we had these oscillations in the last ice age, and corresponding to that there were weather changes as far down into the continent of Europe, where you had differences in the clay and carbon in the clay. So, whether it was poor clay and carbon or it was rich in clay and carbon, that corresponds to the growth and decay of ice on Greenland at multi-thousand year time scales, and that also obviously corresponds to the kind of vegetation that was growing. So, we already saw several examples where you have tundra boreal forests and so on that are latitudinally able to shift based on how cold and how warm it gets. So, on these multi-thousand year time scales, you can see that either warm species are dominating or the cold kind of herbs are dominating. So, there is this coherent variability now going on, not only from Greenland to the sediments and the polar plankton species in the ocean, but also continental climate changes. So, it is beginning to get more widespread in the northern hemisphere, which again shows that on North American continent as far down as Santa Barbara, which is in California. So, you are getting into southern US, very close to the Mexican border, and you can see that the planktonic species here also showed corresponding changes from cold species to warm species. So, how does that work? So, the glacier would have stopped somewhere here, but ahead of the glacier you are changing the climate, making it colder or warmer depending on where the glacier is going, and you are also changing the so called jet stream that we briefly looked at when we looked at the Hadley cell and so on, and there is a separate module on this that you can look up. That jet stream also moves around or splits. When that splits, it brings different kinds of weather, and there is a correspondence with the ice core, of course, and there are also sediment evidences in these coastal waters. Sediments have slightly different processes as opposed to ice cores. Ice cores are collecting gas bubbles and delta 018 signatures in the ice core. Sediments are basically the raining of the biotic material, photosynthesized hydrocarbons or zooplankton, calcium carbonate shells, silica shells and so on. They also have the material that is being brought in by the rivers, which will change in strength, hence the amount of organic matter or other weathered material will change, and we can interpret those. But there are additional complications in the sediments. You always have microbes which are chewing on these organic matter that is coming either from the surface down or from the rivers, and these microbes tend to mix up. There is something called bioturbation. Bioturbation tends to mix up the sediments. So, signatures get merged into multi-thousand years because the layering is destroyed by these bioturbations. So, the resolution can be different, but nonetheless you can see that there are clear signatures of multi-thousand years corresponding to Greenland ice core changes and the biological productivity changes, and so this merges the rainfall changes through river discharge and the biological signatures. So, now did it cross the equator and go into the southern hemisphere, and this is showing Antarctic methane and Antarctic delta 018, comparing it to Greenland methane and Greenland delta 018. So, we are now comparing two ends of the two hemispheres to see if there was any correspondence between the two. If it is, then you have to explain how the signal would go from one hemisphere to the other, where it would have originated, and what are the processes which would transmit it from. Is it the atmosphere or is it the ocean? Typically in the business of climate, they call it atmospheric bridge, which means the circulation changes move the signal from one place to another, one hemisphere to another, or they call it oceanic tunnel, where the ocean circulation is moving it from one location to another. So, again you can see that methane, which corresponds to various biological and terrestrial processes where organic matter can be buried and not respired aerobically, then methane can be produced and so on. So, those signatures are buried, very close correspondence between the Antarctic signature and the Greenland signature. So, it is obviously interhemispheric kind of oscillation at these multi-thousand year time scales, and again the variability between the two hemispheres can be different. Why? You can see that there seem to be many more oscillations in the Greenland ice core than in Antarctica. One thing that can explain this difference is the fact that there is the Southern Ocean. By this time Southern Ocean was fully open, Drake Passage had opened many million years ago. This ocean circulation can smooth out. It is very different circulation than in the North Atlantic. The atmospheric changes and the air-sea interaction changes in the North Atlantic can produce large oscillations at multi-thousand years, whereas over Antarctica the ocean can mix up these signatures just like the sediment bioturbation. Here it is the so-called polar vortex, and the trapping of the air over the Antarctic continent can mix up these signatures and produce much different time scales or smaller oscillations. But you can clearly still see that there are 2,000 to 3,000 year time scales. We will see in a bit more detail that there are 1,500 year time scales, there are 6,000 and 9,000 year time scales, all of which are much shorter than orbital forcing. Okay. So, the question is, once you begin to find greenhouse gases, whether greenhouse gases were forcing these changes, and we will see that actually greenhouse gases were mostly responding to the changes, and then they were becoming a positive feedback, but they do not seem to be forcing the changes. So, what else can force the changes? That is still the question. So, here is carbon dioxide. Again you can see that the variability here is slightly different than the delta 018 from the bird station over Antarctic ice, and again smaller oscillation than the Greenland ice, but very clearly millennial oscillations with some lower frequency oscillations here. So, you can think of these high frequency here, low frequency here, but the low frequency also has smaller scale higher frequencies there, and the carbon is integrating it and producing slower frequency variability. So, you can think of ice growing, vegetation getting buried or being pushed into the ocean or buried under the ice and changing vegetation and so on. So, there is a slow response in the vegetation and carbon. Ice cover over the ocean is going to change the dynamic of exchange of carbon dioxide between the ocean and the atmosphere and so on. So, the signature that is happening faster time scales in ice is not necessarily showing up in CO2. Plus, we will see carefully that since time is going this way, the ice changes are coming slightly before the CO2 changes. Each time the ice changes are coming before the CO2 changes. So, the carbon dioxide is actually responding to ice changes. It has a positive feedback, as you can imagine. If you are warming, then CO2 is increasing, that will increase the temperature, that will melt more ice. If you are growing ice, CO2 decreases, which reduces greenhouse effect, which further cools the temperatures, can facilitate further growth of glaciers. So, it is a positive feedback, but it is not leading the change. So, it is a partner, it is a feedback, but it is not forcing the changes. These are important things to remember. What are the other signatures you can find? So, even in the modern times, now we are shrinking back to about the last 10,000 years, which is essentially the Holocene. We will look at many more issues with Holocene in the historic climate change section, but in this context, are there millennial oscillations in the Holocene? Actually, there are. This is a 2600 year interval in sulfates from ocean sea salt and dust from land on Greenland ice. So, this is Greenland again, and it is showing as we know, as the coldest temperatures set in, the winds get stronger, there is more sea spray, it is being carried further, there is more dust being produced on land, that is being carried further. So, the signatures are definitely there in Greenland, in the Holocene, but they are much smaller and more infrequent than during the Ice Age. Is this good news? Maybe. When there is an Ice Age, there are many more millennial oscillations than in the interglacial, which means in the global warming context, maybe these so-called stochastic or non-deterministic processes are not so important, but we always have to be aware that they are a possibility, and as long as we cannot predict them, we must always keep an eye out for them, right. So, 2 points to be made. I still did not say what is forcing the millennial timescale oscillations in the glacial times, but I am saying they are more and stronger during glacial times than in the interglacial time. Obviously, we have a much shorter interglacial data time series than glacial time series. This can be important for inferring the statistical differences between millennial timescale oscillations in the glacial versus the interglacial, but nonetheless in the 10,000 years of interglacial, there are fewer and weaker millennial oscillations. This is something to keep in mind, because this means that glaciation must have something to do with these unexplained millennial oscillations. Are there other time scales? Jared Bond from Columbia University, the so-called Lamont Doherty Earth Observatory, was one of the first ones to see at the sediments in 2 different places, and this is again depth of the sediment core in both cases, and he is looking at percentage of volcanic versus stained red grains, and he is showing that there are 1500 year time scales. Here is the C14 age in both cases. So, this is very much during the Holocene. So, in the Holocene there are these 1500 year time scales, and these are called Bond oscillations. So, there is this time scales of 10 to 12,000 years where the number of icebergs coming in changed, and that means the perturbation of the meridional overturning changed, because those icebergs that float south are going to get into warmer waters, they are going to melt, they are going to perturb the deep water formation and the meridional overturning circulation. So, those kind of signatures are buried in sediments and ice rafted debris and so on. So, those are called Heinrich cycles. Okay, you can look those up, and there are these multi-thousand year oscillations which are called Dansgaard-Oeschger. Dansgaard-Oeschger, I hope I spell it right. You cannot even read what I am writing, but Dansgaard-Oeschger events. So, these are just the names that we mentioned. Bond cycle, which is like the 1500 year time scale. Heinrich events are the changes in the frequency of glaciers coming into the southern latitude, especially in the North Atlantic, and Dansgaard-Oeschger were the ones who found these millennial oscillations at 2 to 3000 year time scales. Some of them are 6000, some of them are 9000 and so on. So, there are multiple millennial time scales. So, those are the 3 main oscillations. Can we find them in the tropics at lower latitudes? Surely. So, if you look at mountain glaciers in terms of the advance and retreat of at millennial time scales, you can see that there is a 1500 year time scale and there seems to be a 2500 year time scales. These are 2 different data sets, and it also has a multiple time scales. So, there may be 1500 year time scales that is then being somehow integrated to multiples of 1500. So, 3000, 4500, 6000 and so on, and there are processes by which this can happen. So, if you have a 1500 year time scale, as the glacier is growing, it may continue to grow for another 1500 and so on because of internal feedbacks, or if it is melting, it may not finish melting in 1500 years, some other feedback will kick in it will continue for another 1500 years with a burst of growth and retreat and so on. So, these are called things like stochastic resonance, which is kind of a contradictory term if you know, because stochastic means non-deterministic, but resonance is actually a time scale at which things grow by being constructively interfering. So, these are kind of the technical terms. You may not necessarily want to get into those kinds of details in the course, but you can kind of point them out. The main thing you want to point out in this section is really that there are these suborbital time scale oscillations. The term oscillation we are using kind of loosely, right? Are they really oscillations, or are they just events that are kicked off and then they disappear, kicked off again and they disappear? If so, what kicks them off? Nonetheless, we keep using the term oscillations kind of loosely. So, there are all these various time scales that we found in various places from both hemispheres and also down into the tropics. Let us look at the time scales a little bit more carefully. So, what you can do is you can take the long time series you have 100,000 years for the last glacial maximum. The raw time series shows what we could think of as the modulated oscillation that we defined before. With statistical tools, what you can do is you can create a filter. So, here it is looking at this time series and then running some kind of a statistical filter, which means you have low band pass filter or a high band pass filter. So, you pick periods and then you run this time series through that filter and you end up getting this kind of. So, this is a 1470 year time scale filter that has been applied to this time series, and this is the classic modulated oscillation we talked about. We had a sine wave and then we said there is another kind of a wave that is modulating it, or we said it is like the ellipticity modulated precession cycle, for example. And you can see that there are times when these oscillations are weaker and almost disappear, and then there are times when it is much stronger, lasts longer period and so on. So, obviously, there are these modulated oscillations at 1470 years, which is close to 1500 years. And this is important because unless you know what kicks off this kind of change in amplitude, it is going to be unpredictable. So, if you are doing global warming and suddenly the internal oscillation kicks in, it can amplify the global warming or suddenly diminish the global warming. So, we will come back to this in the context of other internal variability. There are internal variabilities at even shorter time scales like the El Nino Southern Oscillation. So, just keep that in mind. These are all given the forcing either from volcanoes or solar radiation changes because of orbital changes and so on. The system can produce these internal time scales because the heat can move from the ocean into the atmosphere or from the atmosphere to melting and growing the glacier and so on. So, these time scales can produce, because of the differences in heat capacity and so on, they can produce these internal time scales, internal variability. So, how are these generated? So, one of the arguments put forth by a famous glaciologist called Richard Alley was that maybe there is always some kind of a fundamental time scale like 1500 years unexplained, and maybe it has this kind of stochastic resonance where, as I said before, where 1500 years melting starts, regrowth happens. I should be going this way. So, growth happens, sudden burst of melting, regrowth and so on to produce multiples of 1500 years. So, this is the stochastic resonance kind of idea. So, minor ice rafting happens in the North Atlantic. So, the signatures are there, but they are small. So, maybe there are small signatures and then it becomes a big signature in multiples of 1500. These are just hypotheses. We still have to show what is forcing them, where the time scale comes from. We do not know that very well. So, I am mostly focusing on this chapter to say that there are oscillations in the system that are millennial time scale, which begins to get close to global warming time scales, and they are non-deterministic. So, you need to be aware of them. So, can you then look for other evidences of what may be forcing them? This is one way to do it. We now go into a little bit more details of how C14 can help us look for these time scales to see if variability in the sun is causing it. So, orbital changes just change the amount of radiation or the distribution, seasonal distribution of radiation in a year, right. What is solar variability? Basically, the sun himself changes over time scales. We will see later on there is a 11-year sunspot cycle, for example, and we will see what sunspots are. So, the amount of energy coming out of the sun can change on millennial timescales as well, okay, because of the flares, solar flares, magnetic knots, and so on and so forth. How would we know in the past when solar variability happened? It turns out that C14, which we said is produced by cosmic rays being deflected by sun's energy into the atmosphere, knocking off a proton in nitrogen and producing C14, and then that C14 decays. We use the assumption that C14 has remained essentially constant as the present, so that you can look at the difference from the present in material that is buried in the sediments or in trees, and how much has decayed gives you the time scale at which those processes happen, whether the sediment signature or the tree ring signature, and so on and so forth. Now, we are going to add a little bit of more complexity and say that when sun's energy changes, the amount of cosmic rays from other galactic bodies is going to change. So, the amount of C14 being produced is going to change. How do we know that? Basically, you can know that by going back to tree rings. You can look at tree rings and you can count the rings, and if the difference between the age you can infer from tree ring and C14 is different, that can correspond to changes in the production of C14. Sounds complicated, but think about it carefully, read about it in the book that is provided in the resources, and you will understand that the solar variability that produces C14 can change, and that can change the amount of C14 that's being produced, and that can show up as the difference in aging between two methods, the tree ring method and the C14 method. And there is another method called beryllium-10. C14 is produced by knocking off proton from nitrogen. Beryllium is produced by another reaction called spallation of oxygen. Just listen to the words since you cannot read it. The spallation of oxygen, it's not a very reliable indicator as good as C14, because when the glacier is growing, the amount of beryllium deposited into the tree ring or the glacier can also change. So, it can confuse the solar variability with the processes internally happening, like the ice albedo feedbacks and so on. Nonetheless, here the C14 and beryllium-10 are being filtered and being looked at together, and you can see that they do match each other. So, here is beryllium-10, which means that it does have the ability to give you the aging corresponding to C14, and both of them together corresponding to the changes in the production of C14. So, the sun is stronger or the sun is weaker, you can have changes in the amount of C14 being produced. Is it complicated? Not really, because we have multiple proxies, multiple dating processes, and the differences are actually telling us something about sun's variability, which is a forcing. If sun's variability is changing, that is a forcing. So, does it work? It turns out that when we looked at all of them together, so this is our cartoon of C14 production, the stream of solar particles deflect the cosmic particles coming from other galaxies. That affects the production of C14 from nitrogen, and that gets buried in everything, like anything that's photosynthesizing, remember, is taking up C14, and that decays. Once it's hidden away, that decays. So, the CO2 that's buried in ice bubbles also has C14 that begins to decay. All these can be used, remembering that C14 is good for only about 50,000 years of dating because of its half-life. Okay. So, the net result is that it turns out solar variability does not explain millennial timescale variability. So, solar forcing is not a cause for these millennial oscillations that are recorded in the ice cores. What else can it be? So, here is a process that was proposed by one of the scientists, which is relying on the fact that as the glacier grows, it tends to push the plate itself on which it is growing, because it is massive amount of weight you are putting on the land, and since the continents float, asthenosphere is plastic, so it can be pushed down or can come back up. You can see that the bedrock that is anchoring or pinning the glacier, and then there is a glacier that is sticking out on the ocean, which is called shelf ice. Okay. As we said briefly before, the sea ice itself cannot grow very thick, because as the sea ice grows, it releases brine, because ice is almost pure water. It releases salt. When it releases salt, the water gets heavier, it sinks, new water comes in, which means new heat comes in. So, unless you have a lake where such circulations do not affect the ice growth, on the open ocean you cannot grow very thick ice, and you end up producing what are called pancake ice. So, if you look at Google and find sea ice maps, you will mostly find these chunks of round pancake looking ice, except in the Arctic where it is almost closed in, a lot of fresh water. Remember, it is easier to freeze fresh water than salty water. If you add salt, the freezing point goes down. So, all those processes have to be kept in mind, but when you have a glacier from land flowing onto the ocean, it can be fairly thick. So, in Antarctica you have much thicker shelf ice than sea ice you can find elsewhere other than the Arctic. So, nonetheless, so here the glacier can slip, and then there is friction, there is melting of the water at the bottom that releases fresh water that further accelerates the slipping of the glacier and so on. But coming back to the spinning point or the grounding line, that gets pushed down, which means the ocean can begin to flow further inward below the glacier, and the warm, remember the ocean water is warm, it is not frozen. So, it is always going to be warmer than the shelf ice. So, the circulation and the movement of the shelf ice that is floating can begin to break off icebergs and break the shelf ice, which means slowly as the ocean keeps invading, it can remove the glacier from this grounding line or pinning point and make the glacier retreat. This is a completely internal process, nothing to do with orbital forcing. It is just an interaction between the bedrock and the glacier and the ocean. So, this process turns out is quite important. It is happening now in Greenland and the Antarctica and other places where the glacier may be flowing onto the ocean, and this is a very important internal process. This explains why the millennial oscillations may be more and stronger when you have a glacial period as opposed to a interglacial period. Okay. So, the other way you can move the signature from the northern hemisphere to the southern hemisphere, once you initiate, let us say northern hemisphere is heavily glaciated, you want to move the signature to the south, then much colder northern hemisphere will move the so called ITCZ or the Intertropical Convergence zone. You can look it up in the other module, and we will come back to it a little bit more when we talk about the monsoon. So, that gets pushed. Essentially the ITCZ is following the heating, because where there is heating there is rising air, that is where the convergence happens, that is where the rain happens. So, as the sun moves, ITCZ moves. So, if it is colder, then the ITCZ moves southward where it is warmer. So, that signature can then be moved across the equator into the southern hemisphere. There are details of why the sign may change and so on. So, you essentially can start with a large Atlantic cooling and generate a small Antarctic warming. So, there is some kind of a bipolar seesaw happening in this kind of process. So, this is essentially one of the processes by which you can move the signature between hemispheres. The other way to do it is, of course, depends on our old friend Samoa circulation. Remember, in the Atlantic, unlike the Indian and Pacific Oceans, water is moving across the equator. So, when the deep water is forming here and sinking, the water to replace it is being supplied from the south. So, if it is warm here and it is not producing as much deep water, if it is warm here and you are evaporating more, you can produce more deep water. So, it is counterintuitive, you have to be careful. Warmer air, more evaporation, more salt, more deep water. So, you can move more heat this way, which means you can make this colder. So, this is another way to produce this kind of north south contrast. On the other hand, if it is colder here, not enough evaporation, less deep water formation, you are not moving as much heat, then you will warm up this hemisphere and you will create again the north south contrast. So, these are the internal processes that are running along all the time. Once some kind of internal variability in ice edge or the feedback between the ice and the bedrock creates these internal time scales. So, these are kind of the feedbacks. To conclude, basically some take home points: there are observed large amplitude millennial oscillations found in Greenland and North Atlantic. That is where we started. Then we found it in Europe, in Santa Barbara, in Antarctica, in greenhouse gases, polar species, tree pollen, and so on and so forth. Its signatures are all over the place. Millennial oscillations are not very well explained, but we pretty much know that they are a product of random behavior within the system. It is often referred to as red noise. Red here corresponds to like the red band of the visible spectrum. It is on the longer wavelength end of the spectrum. So, this is also referred to as a Brownian noise or a brown noise, because Brownian motion is this random motion. If you do not know it, do not worry, you look it up, or just remember red noise. Basically, it means it is stronger at longer time scales than at shorter time scales. So, weather and climate is, let us say, the shorter time scale. It is on millennial time scales and is produced by internal noise in the system. So, understanding the cyclic and non-cyclic solar variability and climate relation with climate variability is weak, basically because we cannot very well reconstruct past solar variability and track the processes that begin a kickoff. But we will see, already we mentioned that there is a relation between precessional change and monsoon, for example. So, there is relation between solar forcing and climate variability, but there are time scales where at millennial time scales maybe we do not understand it so well. Natural variability in the northern ice sheets probably started off the millennial oscillations, and they were transmitted to Antarctica either by the atmospheric bridge, where the circulation can transport the signal from one hemisphere to the other, or it is through this ocean thermohaline circulation. Methane and carbon dioxide also have a signature of these millennial oscillations, but as we saw, the timing does not work out in terms of them being a forcing. They are a feedback. There are slight differences in the way methane is influencing the feedback versus carbon dioxide, but that is a kind of detail you may not necessarily worry about. There are reasons why the CO2 time scale feedback tends to dominate, but if you just remember that greenhouse gases responded to changes initiated by some other forcing, and then they were a positive feedback. So, they were not the forcing agents, but they were definitely feeding back to the changes that were initiated by some other forcing agent. So, we essentially learn millennial oscillations to say that there are very strong evidence of these oscillations. They are very strong during glacial times, they are not so strong during interglacial times. They could be important for global warming, obviously, because they are internally generated and they are non-deterministic, which means they are not easy to predict. Does that mean models do not have it? Of course not. The models that have ice sheets and can move the bedrock and can create these meridional overturning circulation changes and so on they will have these time scales. So, the models are run for thousands of years and we look for these internal time scales. So, that is for another day, but this is the topic: millennial oscillation, non-deterministic, may not be oscillations, but nonetheless they are important and visible in all over the world. See you next time.